continuously down the image, adds the signals together to emphasize any echoes that have been received at a given depth. And it just brings into focus, it sharpens the detail of anything that we see at those respective depths. So it's very easy to do with a fast computer. So it doesn't require anything extra on the transmission side. You just transmit as you normally would, detect as you normally would, then you process the data in this special way. So, describe, sorry, yeah.
So yeah, isn't it also focusing on width? Because the curvatures are symmetrical. So we also focus on width, not only depth. Or not?
I'm not sure why width.
Yeah.
I mean, try to make it narrow in this direction.
Well, I mean, not narrow, it's just the absolute width. Because the curvatures are symmetrical. So we just focus
I mean,
on
if the point is off axis,
you have to change the curvature there. Or not?
it would. It would, but I don't think this would have an effect one way or another. I think if this was off axis, well, ideally, your emitted beam would be as narrow as possible, such you wouldn't get any echoes if something's off axis.
So we want to focus off axis, then you have to change the curvature.
You would. I don't know that that's ever done. But I do see what you mean.
We don't have to mention it though.
No, no. It's something for getting at different depths as opposed to making it narrow and axis. Okay, having described that, I think then describing that in words on an examination paper is actually quite difficult. It's difficult to pick up 4 marks for that question in the limited time you have to answer it. Okay, the next part is a calculation, which I think is the hardest part of this exam question. It says, consider dynamic receive focusing applied to signals acquired from a group of 15 transducer elements of a probe described in part B. To focus at a depth x, the signal obtained from the central element of the group is electronically delayed by delta t, which is a function of x, before being added to signals from the 2 outermost elements of the group. Derive an expression for the variable time delay delta tx as a function of x. Note that if you didn't know what dynamic receive focusing to answer the previous question was, you've pretty much given the answer in the second question. So you could almost write that as your answer to the first part and probably pick up several marks. Okay, so to answer this question, here I've drawn 15 elements in the group, and what the question is asking me is for echoes which are originated at a depth x below the center of the group, what is the delay that I need to add to the signal received at the element on the very end in order that it can be added or arrived at the same time as the signal from the central element in the probe. So you can see as the wave moves back up, it's going to arrive at the central one before it arrives on the outer one, and we need to shift that signal back by a certain amount such that it arrives at the same time as that one. So, it's a relatively simple bit of geometry you need to do, calculate that delay. First of all, what is the width of each element? It's easy to calculate from the question. We have 120 elements over 80 millimeters, therefore the width of each element is 2/3 of a millimeter. Now, my right angled triangle there, this distance here between the center of the central one and the center of the outermost one, that is a width of 7 elements. 7 times 2/3 is 14/3. So that distance there is 14/3 millimeters. Now we have a right angled triangle. We know 2 sides, therefore we can calculate the hypotenuse, and I is going to be equal to the square root of x squared plus 14 over 3 squared. So that is the distance between that point there, the point at which we're obtaining our echoes from, and the centre of the outermost element. The question asks for that time shift, the temporal delay that we need to apply in order to get the echoes to coincide. So we need to know the difference in the distances between that distance and that distance. Well, that is simply equal to that distance minus that distance, which is our hypotenuse there, minus x. So the extra distance travelled by the signal, the outermost, recorded by the outermost elements, is that thing. Now time equals distance divided by velocity, and therefore delta t, here delta t is going to be equal to that thing divided by c. So that is my expression for the time delay that we need to apply to the signals acquired from that element in order that it coincides with the signal obtained from the outermost element. It's a relatively straightforward derivation, although not necessarily very easy to do in the sound situation. And the last part says sketch delta t as a function of x over a range from x equals 10 to x equals 80 millimetres. That's hard to do if you don't get the answer right, but the sketch does look something like that. So that is just simply, just put some numbers in here. So put x equals, I don't know, 10, 20, 30, up to 80, or maybe even every 20 would be sufficient. And plot delta t as a function of x. And you should get something that looks something like that.
Given it's a sketch, would you be expected to have all the numbers on the axes and all that? Or is it a shape reference?
I wouldn't expect that level of detail, no.
But would you, for instance, expect the numbers on the end points? Or just the shape?
I think I would expect at least one number on this axis. Yeah.
Okay.
Yeah. Yeah. If you had like 500 there, that would be fine.
Yeah.
Obviously that's got to go to 0 to 80 because the question asks for it, so that almost doesn't need labels, but you'll expect at least one.
You get set the circuit by the expression the cos and tan minus 1. I think it's right.
I can check it, but yeah, if it's right.
I think the thing is you dramatic is the tan.
Yeah. That's fine.
Because it's taking into account that
Yeah, of course, yeah.
oh, it's further.
There's different ways.
Yeah. Right, so you have to subtract 2 to get the difference between them, to get your time delay,
Okay,
which is why you use to get
question
time
4.
delay.
Okay, first part of this question is about ultrasound, second part about MRI. Question asks, says, a hollow steel needle is inserted into a female breast in order to drain fluid from a small cyst. A phased array ultrasound probe is used to navigate the needle towards the cyst. With the aid of a suitable diagram, describe the likely appearance of the needle and the cyst in the image, name and explain the artifacts. I remember last year marking this part, and the variation in diagrams I got was enormous. 50 students in the class, I had 50 completely different diagrams. I expect some variation, but maybe not nearly as much variation as I got. Something like this. What I'm really looking for is the needle will be an extraordinarily strong reflector. Steel, being a solid, is going to reflect the ultrasound very strongly indeed. So anything below the needle in your image is going to be dark. So depending on how you've oriented your needle doesn't really matter. You've got to show that it casts an acoustic shadow. OSHA should say that you're told it's a phased array. Phased array generate triangular images, not rectangular images. That's another, where there's another point to be picked up. So those students that drew rectangular images probably lost this half mark. So see a sector scan for a phased rise, but a small footprint is going to broaden out. The cyst itself, cysts are little pockets of water, liquid, mostly water. They are relatively low attenuating compared with the surrounding tissue, and thus echoes that travel through the cyst are going to be less absorbed than they would have been had they not gone through the cyst. Thus, tissues beyond the cyst appear enhanced in the image. We get more intense echoes from this region because they pass through the cyst twice, in fact, and therefore they're less attenuated. So you get what's called acoustic enhancement. So, to get the full marks, certainly want to see an acoustic shadow, and the naming, actually describing acoustic shadow, it asks you to describe any artifacts observed, and also the acoustic enhancement, which is a very useful, very powerful diagnostic in itself. It's the way that we distinguish cysts from other forms of lesions in the breast. Okay. Clarify why ultrasound imaging is normally able to distinguish between the cyst and a solid mass, such as a tumor. Well, really, I'm not sure it's worth more than a mark, maybe only half a mark. Just need to say that it is a characteristic of cysts that we get this acoustic enhancement, which is not observed for a more solid lesion such as a tumor. Okay, question 4b. Briefly explain how the occurrence of so-called grating lobes can result in artifacts in ultrasound images produced by array transducers. Okay, so grating lobes. First, let me just reiterate what we call side lobes. An ultrasound transducer ideally just produces one main beam. All the ultrasound should ideally be confined to a narrow beam which is steered backwards and forwards by some mechanism or other. And any echoes that are obtained are assumed to have come from that beam. In a poorly designed transducer, the physics of ultrasound beams enables for some ultrasound power to go off at very specific angles to that main beam. These are known as side lobes. And a well-designed transducer will make the intensity in those side lobes as low as possible. It's never exactly zero, but it can be designed such that it's almost negligible. If any echoes are obtained by pulses which have travelled within the side lobes, then those echoes will assumed to have come from the main beam. So in this situation here, anything that's reflected on that object here will have assumed that those echoes will have occurred within the main beam. Therefore, that object will get placed over here, as shown in this diagram here. Well, for linear arrays and phased arrays, we can also get these side lobes, which in this case are known as grating lobes. The physics is actually exactly the same, though it's probably easier to understand in the case of these array planes. Okay, so to illustrate the occurrence of these grating lobes, let's consider we have these 5 elements all being pulsed at exactly the same time. So no delays here, they're all being pulsed at exactly the same time. Well, a pulse consists of several oscillations of ultrasound intensity. So we have an intensity profile which contains, let's say, 4 or 5 oscillations in intensity or impression. So these black lines here represent the peaks in this intensity profile obtained from these 3 elements. I could have done diagrams for the other 2 as well, but just to make the diagram a bit less complicated, I restricted it just to those 3. Now, as I described in the lecture when I was telling you